right. Well, I guess we should go ahead and get started. We've got several of you in here, not all of you, of course, but it looks like most of you have chatted me your first and last name, so that's good. I did want you to go ahead and get that started. Last time we met, we were talking about chapter 10, and I completed the last example. There's, of course, plenty of other examples that you can look at in the book or on my YouTube channel. As well as links in the modules. I actually need to update that as well. I discovered that some of the videos I had listed for this week's module for Chapter 11 are missing. I put all the ones that I normally recommend for Chapter 10, but Chapter 11 is missing. So I'll be filling that in tonight and tomorrow. But those are the video examples that I think are most helpful. We're starting right now in Chapter 11. Chapter 11 is called Angular Momentum General Rotation. And a big part of this is now that we've completed the understanding of Newton's first, second, and third law and Newton's law of gravity. Uh, and then once we introduce rotation, we have now the ability to actually study how things actually move according to the laws of physics. So, for instance, if I wanted to throw this TCC uh, thermos, if you will. If I wanted to throw it, and I'm only using that because it happened to be laying on my desk, I don't have to pretend it's a point object. Because the problem with a point object is if I threw it, then it would have a split second that it lands, and that's it. But in reality, it's a little different than that because this thing has a physical size about it. The center of mass, if it lands like this, the center of mass would still not actually hit the ground at the end. But if you tried to calculate it as if it was a point particle, you'd be making a calculation as if the center of mass landed, when in fact, if it landed like this, it would land here and the center of mass would still be basically one radius above the surface of the ground. So that's not very helpful. But in addition to that, it could possibly land not like this or like this, which that way would cover, but it might actually land like this or like this or like this or like this, all those different positions. So we now have the ability to work out where the center of mass will be at any time later, but we could also imagine just some other random point. Let's say the center of mass is here, and let's maybe imagine there's a dot right here on this. I can actually figure out using rotational motion that we've learned so far. I can basically construct a vector that points from the center of mass to that specific dent in the or mark on the thermos bottle and predict what angle that vector makes with the horizontal at any point in time, so that I can not only tell where its center of mass is, I can tell its orientation at any time later. So, because of that, I can use that orientation to tell me when it actually hits the ground. Is it going to hit with this edge down, or with this edge down, or with this edge, or this edge, or this edge? So, I can tell a lot more details about it. That is sort of the quote unquote holy grail for classical mechanics, is what exactly or how exactly is the thing going to move? How's it going to land? Is it going to land flat? Is it going to land on a corner and bounce up real high? Or is it going to land on an edge and slide? All that kind of stuff. All that we can now do because we have the ability to not only study point particles, but physical objects. In addition to that, we need to understand angular momentum, which we haven't covered yet, even though I've hinted at it several times. And that's what we're going to do now. So I'm going to go ahead and share my iPad screen with you all, and we'll get started on the examples from the book or something closely there related. And the screen should pop up any second now. So the first thing I want to remind you about is we had Newton's second law, which we initially recognized as the summation of the forces is equal to mass times acceleration. And we, of course, later learned that that wasn't exactly completely correct. This isn't what Newton said in his Principia, but as long as the mass of the object we're studying, the m and the F equals ma, as long as that's not changing, then this is a fairly accurate way of, or actually, it's a very accurate way of predicting the behavior of an object based on the laws of physics. But the rotational analog to that is the summation of the torques is equal to the rotational analog of mass, which is the moment of inertia, times the rotational analog of acceleration, which is the angular acceleration. So that's Newton's second law of motion. In parallel are basically how it corresponds to the linear version. So F equals ma is analogous to the summation of the torques equals I times alpha. Now we also learn that the summation of the forces is equal to what Newton actually said, which was dp dt, where p is equal to mass times velocity. Now, all of this stuff that I'm talking about right now is all dependent on us studying classical physics. If we're talking about things moving on the order of a percent of the speed of light or higher, or if we're talking about things whose mass is so large, if we're talking about things whose mass is comparable to the sun and stuff like that, we're probably going to have to use general relativity or special relativity. If we're talking about things that are so small that we're interacting with atoms and molecules, then we're going to have to use quantum mechanics. But as long as we stay away from those, the Newton's laws of physics should work just fine. But here is the rotational analog for that version of Newton's second law, and your textbook author takes a little time to sort of derive these. The rotational analog of this one is the summation of the torques is equal to dl dt, where L is the angular momentum. And one way you can think of angular momentum, if you're talking about a particular body rotating about some axis, we're actually talking about a object rotating as opposed to revolving. To get you straight on those words, revolving is what the Earth does around the sun, and rotating is what the Earth does about its axis. Revolving is what Jupiter does around the sun. Revolving is what Mars does around the sun. But again, rotation is what Mars does about its own axis and what Jupiter does about its own axis. So if you're talking about something rotating about its own axis, which we call rotation, then we can say L, the angular momentum, is the rotational analog of the linear momentum P. And the linear momentum, of course, was mass times velocity. So the rotational analog of mass is moment of inertia, and the rotational analog of velocity is angular velocity. And we use the right hand rule, as we've talked about before, to decide what the direction of that angular velocity is. So, for instance, if we're seeing something's rotating like this, then we say, okay, let's take our right hand and make my fingers curl around in that same direction. Now my right thumb points in the direction of that omega vector. That's key. Now, if we're talking about instead of rotation, revolution, then L is equal to R cross P, where again P is equal to mv. So that's the angular momentum, for instance, that the Earth has as a result of orbiting around the sun, or that's the angular momentum that the moon has as a result of orbiting around the Earth. Then the L equals I omega is the angular momentum that the Earth has as a result of rotating about its axis, and L equals I omega is the angular momentum that the moon has for rotating about its axis, so on and so forth. The big picture on all this is hopefully you all remember, because I told you this is one of the things you should memorize. Can anybody tell me under what conditions linear momentum is conserved? Anybody? And y'all can either just speak it out right or you can type it in the chat. I just opened up the chat again. But any of those you want to, just let me, you can say it any way you want. So just let me know what is the condition necessary for linear momentum to be conserved. Okay. So linear momentum being conserved means the linear momentum is a constant. If you look at dp dt equals the summation of the forces, you see that if the summation of the forces acting on the system, notice the wording here, I'm talking about the system as opposed to a single object. So if the summation of the forces acting on a system is zero, then dp dt of the system is equal to 0, and that implies P of the system is equal to a constant. And that is what we mean by conservation of linear momentum. The total momentum of the system is a constant. So you have a momentum before a collision, for instance, you have a momentum after the collision, and if the net external force acting on the system is 0, then momentum will be conserved. Now that you know that, can someone tell me under what conditions would angular momentum be conserved? So here's my big question. Under what conditions would angular momentum, L, be conserved? Anybody have an answer to that? Feel free to type it in the chat or just say it out loud, in other words.
Would it be like when the vector r and vector p is constant?
Well, that would actually absolutely be true. Yeah. But that would be a little too restrictive. Can you think more along the lines of the parallel of what I just did with linear momentum? You're absolutely right. That is that's essentially the definition of conservation of angular momentum. But I'm looking for something analogous to what we just used to conclude that linear momentum was conserved.
What did the r variable and the p variable mean? I want to write the
Ah,
notes.
very good. Yeah, that's good. And yes, Joseph, you're right. Good job, as well as Anna as well. Y'all both got it right. So the L is a vector, or the L is R cross P, and R is a vector that points from the origin of whatever your coordinate system you're using is, and it points from there to the actual particle whose momentum is m times v, and P is the actual m times v. So
Okay, got it.
does that make
That clears
sense?
it up. Yeah.
Yeah. So, for instance, a typical coordinate system for us to use in our solar system would be the center of the sun is pretty much sitting still. In actuality, it doesn't. The center of the sun is sort of oscillating like this, moving on the order of a couple meters, but not a huge amount. But we generally can think of the origin of our coordinate system as the center of the sun, and you would imagine the r vector pointing from the center of the sun out to the center of, let's say Mercury, because Mercury doesn't have a moon. That makes it a little less confusing. Now, the vector P is the mass of Mercury times the velocity of Mercury at any point in the orbit. So you're doing a cross product of those. Does that help too, Michelle?
Yeah, that does. Thank you.
No problem. So the analog is exactly what Anna and Joseph said. The analog is if the summation of the torques is equal to 0, then dl dt equals 0, and that implies that L is equal to a constant. And remember, L being equal to a constant is the very definition of conservation of L, which in this case is linear momentum. So that's really what we mean. Whenever we say a conservation law, we mean that quantity is equal to some constant. So conservation of charge means if you take all the charge that you're interacting with in your system and you add them all up, you count, the pluses as positive E, say, and the minuses as negative E, and you add all them up, you'll get some number that's either positive or negative, and then you let some major occurrence occur, and then afterwards you do the same thing, and it better come out to exactly the same answer. That's conservation of charge. That's the same thing with conservation of linear momentum, the same thing with conservation of angular momentum, same thing as the conservation of energy. Okay, so that's the bare necessities of what we need to do. Now it's just a matter of figuring out how to actually apply this. So again, I want you to realize that the chapter opening question is very helpful. That's always something you should do before you go into reading. The contents of this chapter are subsection 1, angular momentum, objects rotating about a fixed axis. That's the L equals I omega case that I was just talking about. 11.2 is vector cross product, torque as a vector. We actually did that. I did that in chapter 10. That's part of the reason chapter 10 took so long, as I covered it in chapter 10. So we won't even be messing with that section. 11.3 is angular momentum of a particle. That's the R cross P that we were talking about. So that's again another cross product. 11.4, angular momentum and torque for a system of particles. That's general motion. That's an actual derivation of Newton's second law of motion, as I was just showing you. The summation of the torques equals dl dt. 11.5 is angular momentum and torque for a rigid object. For a rigid object, all we mean is you take one point in the object and another point in the object. Maybe they're specific atoms, that would be fine. And if you draw a vector from one of those atoms to another one of those atoms, then that vector might actually change its location and it might change its orientation, but it's never going to change its length. That's what makes it a rigid body. And in fact, you can do that for every atom relative to every other atom in the whole body. And if it's truly rigid, that's going to be the truth about every one of those little vectors. So that's what a rigid object is. 11.6 is conservation of angular momentum. 11.7 is a spinning top and gyroscope. That talks about uh, precession. So if you've ever taken a quarter and give it a pluck and it starts to spin, what you'll see is it spins pretty good, but it's also doing this sort of wobbling thing like that. That's called precession. And your book talks about it. It even gives you equations that we can use for that. But that's an optional section, so I'm not going to quiz you on that. The same thing with 11.9, the Coriolis effect. That's an optional section. I'm not going to give you any test questions on that, but I'm okay with you doing them for homeworks. And I tried to get the practice questions out of the practice test for it, but they still might be some in there. 11.8, rotating frames of reference and inertial forces. That's just a conceptual area that I need you to read. So the last three sections, 11.7, 11.8, and 11.9, you can sort of, I don't want to say ignore the examples, but I want you to think that you can ignore the examples in the sense that I'm not going to make you solve a problem like those that have been done. Okay. So we're going to continue on now. And I want to point out, for instance, what angular momentum conservation means. As I already told you, the angular momentum being conserved means the angular momentum is a constant. So one type of conservation of angular momentum conservation is L1 equals L2, and it's technically a vector quantity, so you can do that. What that means, though, is I1 omega 1 is equal to I2 omega 2. So, for instance, if you're considering something like me sitting in this office chair, I could spin and I'm going to have a moment of inertia, which is related to how my mass is distributed within this chair. And if I sit with my arms pulled in really tight against my side and keep my feet tucked up under my butt and my knees really close together and all that, then I'm sort of not putting any of my weight really far out. That would result in me having a low moment of inertia. The mr squareds that I'm adding up are going to add up to fairly small because all the r's, the distance between the axis of rotation, which is basically the center axle of this chair, the distance between that perpendicularly out to whatever body part it is very, very small. So if I started spinning like that, I would have a certain angular momentum. That angular momentum would be that moment of inertia I that we could calculate using a series of mr squareds times that omega, which might be a certain number of revolutions per minute, or it might be a certain number of radians per second, or whatever. But as I was spinning, if I was going fast enough that I could keep spinning for a while, I might decide to stick my arms out like this and then spread my legs really far out as well. When that happens, you see all of a sudden I've got mass times r squared is really big for my elbow, for my bicep. It's even bigger for my forearm, even bigger for my wrist, even bigger for my hand. Same thing with my thigh, with my knee, my calf, and my foot. So all of that results in the eye getting really big for me after I spread. If the eye got really big and the I omega has to be the same, then that means the omega is going to have to slow down. So that's why you see when an ice skater has her arm or his or her arms up above their head like that or down by their side like this and their legs are really closed in, they're spinning quite rapidly. But when they bring their arms down and do this, it slows down. Or if they maybe get in a swan position, say with their foot sticking out the side, then that slows them down as well. So really what happened is you can imagine the moment of inertia getting really big, and then to compensate for that, you have to have the small moment of inertia has to have a big angular velocity. So in other words, the two numbers, which could be, for instance, let's say 25 times 4 gives you 100. Over here, we could say, well, what if I went from 25 to 12.5 for the moment of inertia? Well, that would indicate that the uh, angular velocity would have to go up to 8 because 8 times 12.5 is 100. So that's really what conservation of angular momentum is, at least when we're talking about rotating as opposed to revolving. Revolving is a different beast altogether. If we want to talk about revolving, so this was all rotation. If we want to talk about revolving, then I will use this example. We're going to imagine an elliptical orbit for a planet, say, and let's say this is our sun. And what we might have is a planet right here. This position is called perihelion. If it was an object orbiting our Earth, it would be perigee. But since it's orbiting Helios, our sun, it's perihelion. And this distance right here is called r perihelion, which I'll say r sub ph. And the velocity that it has right there is called v perihelion. If you wait half a year later, a year for that particular planet, for instance, then the planet will be over here. And now the distance from here to here is r aphelion. So this position is called aphelion. Again, if it was something orbiting our Earth, it would be apogee, APOGEE. And here we have a small velocity, v perihelion, but a large angular or a large distance, r aphelion. So angular momentum L1 equals L2 is going to give us basically r aphelion, or let's say r perihelion, times m times v perihelion is equal to r aphelion times m times v aphelion. Notice that's just the cross product, r cross p, in the cases where, notice as I've drawn here, the actual r vector and the velocity are perpendicular to each other. Because of that, r cross p is just r times m times v because p is mv. Does everybody follow that? Anybody have any questions on that? Okay, so that's a way you can actually solve a conservation of angular momentum problem for the orbits of planets. You notice the mass, a planet's mass doesn't change as a result of being at one side of the orbit versus the other side. So you could actually divide through both sides by m, and you just get r times r sub ph times v sub ph is equal to r sub ah times v sub ah. And that always works. If you try some other points other than aphelion and perihelion, it's going to be more complicated because the r and the v are not going to be perpendicular to each other, and therefore the r and the p are not perpendicular to each other. But that's the two scenarios that we can use for conservation of momentum. Either I times omega equals a constant, or r times m times v equals a constant. Anybody have any questions on that? So your book tells you this way. It says the total angular momentum of a rotating object remains constant if the net external torque acting on it is zero, and they give it to you in terms of I omega equals I zero times omega zero equals a constant. So let's try an example. Example 1-1. Excuse me, example 11-1. I said 1-1 because I just saw one of the three numbers, I guess. I don't know. Anyways, what we have here is a table, and we're looking at the table, and there's a hole in the center of the table, and then there's a string, and attached to that string is a mass M, and this mass is following a circular orbit like this, and the radius of this particular circular orbit is R. We're going to say R1 is 0.80 meters. R2 is going to be 0.48 meters. And we're going to say it has a velocity V1 when the radius is R1, and V1 is equal to 2.4 meters per second. Okay. What we want to know is if R goes from R1 to R2, what will be, oops, will be V2? That's the big question. Okay. So you can try this yourself. You can take, for instance, and drop a string through a straw and then hold the straw up and have a mass tied to the end of the string, and you can get it swinging over your head like this. And then all you have to do is pull the string down here. And what you'll see is as that radius decreases, angular momentum is going to be conserved because you're not actually applying a torque to the system. You're actually, the only thing you did was pull down on the string, and that meant a force that went radially, so it can't actually supply a torque because literally the force is directed at the rotation axis. So it's going to cause it to speed up like that. And in fact, it'll normally cause the string to break if you pull it far enough. So that's what we're trying to calculate here. So what we're going to do is say I1 omega 1 is equal to I2 omega 2. And we know that the moment of inertia for a object of mass m out a distance r is just mr squared. That should make perfect sense to you. If not, it's also in the table of period of the moments of inertia. So in this case, we're going to say m times r1 squared times omega 1 is equal to m times r2 squared times omega 2. But we're also going to use the fact that V is equal to R omega, so that omega 1 is equal to V1 over R1, and omega 2 is equal to V2 over R2. Now we can plug all that in, and we'll get M times R1 squared times V1 over R1. Yes, oops, everything
Oh,
left.
sorry. Yeah, the screen went black.
Okay, so
Yeah, it's back.
the left-hand side becomes m times r1 squared times v1 over r1. The right-hand side becomes m times r2 squared times v2 over r2. I think you can see that one, the mass cancels out on both sides, and two, the exponent cancels out on both sides, like this. Actually, I should probably do it like that. That way it looks like an entirely different thing there. So with all that, now what I have is R1 V1 is equal to R2 V2. And notice that's exactly the form that I started off with when I was doing this. The M can just, of course, be canceled out, but that's why I said this is conservation of angular momentum for the planet at two different points in its orbit. So we've got the same equation. Now I can work all this out. All I've got to do is put in or solve for V2, and that means V2 is going to be V1, or excuse me, is going to be R1 over R2 times V1. And of course, R1 is 0.80 meters and R2 is 0.48 meters. Notice that this is like 8 times 10. It's actually 8 times 10 divided by 100. And this number at the bottom is like 8 times 6, but also divided by 100. The main thing I'm doing that for is because the 8's cancel out and I get 10 over 6, which is also 5 over 3. Okay, so 5 over 3 means I'm basically going to take this velocity, which was 2.4 meters per second, and I'm going to multiply it by 5 over 3. So 2.4 meters per second. If I multiply 2.4 times 5, that gives me 10 plus 2, that'd be 12. And then I divide 12 by 3, that gives me 4. So the new velocity will be 4.0 meters per second is equal to V2. So don't worry yourself about the arithmetic tricks that I was pulling there. That's just me trying to avoid pulling out a calculator and making my fat fingers screw up. So anybody have any questions on that? Okay. There's another problem here. This is 11.2, and this is about a clutch. And I'm proud to inform you all that I know that the word clutch sometimes means a woman's small handbag. That's because I have a wife and I watch TV. But this is not the clutch we're talking about. Okay. This clutch is the clutch like you have in a stick shift of a car. And what they mean by that is basically two plates that, when sandwiched together, the friction forces are going to cause them to rotate and move at exactly the same rate. Uh, in terms of your transmission of your car, you can imagine the clutch is the little pedal that you push in, but in actuality, you're pushing that pedal in. Basically, just allows a spring loaded mechanism to force two plates apart. And then once you let go of the clutch, they slam back together, or some other plate slams back together with one of those plates, that sort of thing. So in this case, they say a simple clutch consists of two cylindrical plates that can be pressed together to connect two sections of an axle as needed in a piece of machinery. The two plates have masses MA equals 6.0 kilograms, MB equals 9.0 kilograms with equal radii 0.60 meters. They are initially separated. Plate MA is accelerated from rest to an angular velocity omega 1 equals 7.2 radians per second and a time delta t equals 2.0 seconds. They want us to calculate the angular momentum of M sub A. Part B, they want us to calculate the torque required to have accelerated M sub A from rest to the omega 1 that we just mentioned. And then part C is next, plate MB, initially at rest but free to rotate without friction, is placed in firm contact with the freely rotating plate MA. And the two plates then excuse me, both rotate at constant angular velocity omega 2, which is considerably less than omega 1. Why does this happen and what is omega 2? So I'm going to write down the information we were given. M sub A is 6.0 kilograms. M sub B is 9.0 kilograms. What we found was omega 0 was equal to 0 radians per second. That is the preferred measure to put radians in, but I mean to put omega in, but it could also be revolutions per minute or cycles per second or stuff like that. But normally, when we have the phrase cycles per second, that normally refers to hertz, and that's the quantity F that we call frequency. And omega and F are related through omega is equal to 2 pi times the frequency, or omega equals 2 pi F. So I just want to point that out because that's going to come in handy later. I'm going to say the omega final is the omega that they're talking about, and they called that omega 1. I'm just calling it final so we'll know what we're talking about. That's 7.2 radians per second. We also know the radius is 0.60 meters. and the change in time, the amount of time required for it to go from 0 radians per second to 7.2 radians per second is 2.0 seconds. As I said, they wanted to know the angular momentum, so L initial is equal to question mark. And that's specifically the momentum of just the part A. Even though we're treating the system as MA and MB together, we're going to we're going to treat the whole system as MA and MB, because if we didn't do that, then when MB lands on MA, MB is going to be applying a torque to MA, and since it's applying a torque on MA and we're treating MA as our system, then conservation of linear momentum would not be true. But if we treat the system as MA plus MB, then MB applies a torque to MA, doesn't matter because that's an internal force. So that's the key thing that you want to understand here. For part B, it says the torque. So we want to calculate the torque. That's the question mark. And then part C, they want to know omega 2 is equal to question mark. Okay. So first off, L initial is equal to I times omega. They said this clutch was in fact cylindrical. I actually did the derivation of the moment of inertia for a cylindrical object, and that's 1/2 mr squared. So in this case, it's going to be 1/2 m sub a times r, what we called r0 squared. That's the moment of inertia, and then omega, what we called omega final, what the book called omega 1, is the omega. Now I'm just going to plug these figures in. I got 1/2 times 6.0 kilograms times 0.60 meters squared times 7.2 radians per second. When I do all this multiplication, I get zero point 0.5 times 6 times zero point 0.6 squared times 7.2, and that gives me 7.78 kilograms meters squared. This is the units of angular momentum, so I want to make sure you guys are aware of it. Notice I'm working it out. It's kilograms times meters squared divided by seconds. So that's the actual units, and that's the initial angular momentum of the disk MA, for instance. But it's actually the same thing for the system, because the other one has all the moment of inertia and all that good stuff, but its velocity, its angular velocity is 0. So that's part A. Anybody have any questions on that? Your book called the answer 7.8. I'm carrying an extra sig fig, so you can see it does round to 7.8. Now for part B, they want us to calculate the torque. Well, torque is equal to I times alpha, so I need alpha. Well, alpha is equal to omega final minus omega initial divided by delta t. Well, that's equal to 7.2 radians per second minus 0 radians per second divided by 2.0 seconds, and that gives me 3.6 radians per second per second. So that's our actual angular acceleration. Now I can use that to calculate the torque, because the summation of the torques, which I actually should have wrote that there as well, the summation of the torques, ooh, got myself into a heap of mess by trying to write that in there. So the summations of the torque is equal to I times alpha. So that means the net external torque on the system must be equal to that. So I've got 1/2 times 6.0 kilograms times 0.60 meters squared times 3.6 radians per second per second. So now when I do this math, I get 0.5 times 6 times 0.6 squared times 3.6. Oops. I need to hit exit, and I've got to find my exit button now. Where's my exit button? Yep. Yep. Oh, there it is. Okay. 6.6 times 3.6. Yes. So this gives me 3.89, and that unit comes out to be kilogram meter squared per second squared, which is a Newton meter, or as your book calls it, that's a meter Newton, is equal to the torque. So that's our answer to part B. Anybody have any questions regarding that? All right, so now we're going to use conservation of momentum to figure out what the new final velocity is. This is exactly analogous to the two train cars. Remember, we had a 10,000 kilogram train car moving at 8 meters per second, runs into a stationary 10,000 kilogram train car. And then they stuck together, and they asked you what the final velocity of the two stuck together is. That was conservation of linear momentum, but in the exact same way as this. This is just where we're dropping something on it, and now the two are going to rotate at a slightly slower rate. So L initial is equal to L final gives us, and I'm not going to go back and recalculate L initial. I'm just going to take that value that I had, which was 7.78 kilograms meters squared per second. That's going to be equal to the new one. And notice now, instead of one cylinder that has a mass of 6 kilograms, it's one cylinder because the two stuck together makes a cylinder as well. And they have the same radius, so it's just the same thing. So now it's 1/2 mr squared, but the m is 6 plus 9. So this is going to be 1/2 6.0 kilograms plus 9.0 kilograms times R, which is 0.60 meters squared. So that's my I, and then my omega final, which is what we're asked for, omega 2, that's what goes there. So now I can go ahead and say 7.78 kilograms meters squared per second is equal to zero point 0.5 times 15, because 6 plus 9 is 15, times zero point 0.6 squared, and that's the whole thing. That gives me 2.70 kilograms meters squared times omega 2, and that tells us that omega 2 is 7.78 divided by 2.7, which gives me 2.88. If you look at the units now, you see that all that's left is radians per second, and that's part C. Anybody have any questions on that one? And all these answers match. Your book had 7.8 kilogram meter squared per second for part A. I got 7.78. They had torque was 3.9. I got 3.89. And they had omega 2 is 2.9 radians per second. I had 2.88. So they all match even up to the sig figs. Here's a nice problem. I didn't do this in my face-to-face class today, but I decided I'm going to go ahead and do it now. So it says astronomers detect stars that are rotating extremely rapidly, known as neutron stars. A neutron star is believed to form the inner core of a massive star collapsed under its own gravitation to a star of very small radius and very high density. Before collapse, suppose the core of such a massive star is the size of our sun, which is on the order of 7 times 10 to the fifth kilometers, with mass 2.0 times as great as the sun, and is rotating with a frequency of about one revolution every 100 days. If it were to undergo gravitational collapse to a neutron star of radius 10 kilometers, what would be its radiation frequency? Assume the star is a uniform sphere at all times and that no loss of mass occurs. Uh, there is usually a little bit of loss of mass, but it doesn't really matter too much. So in this case, this is example 11.3. What we have is a sphere. So I sphere is 2/5 mr squared. I just happen to know that off the top of my head. But as I told you, future practice tests and future online tests and future face-to-face tests will actually have the period a table of moments of inertia that we can use as well. So I've got that. I've got R1 is going to be 7 times 10 to the fifth kilometers. And I can keep kilometers, that's fine because the other one's in kilometers as well. So I'll just leave it like that. R2 is going to be just 10 kilometers. And I'm assuming they're giving me two sig figs on everything at least. We also know that the mass M is 2.0 times the mass of our sun, and that's the symbol we use for our sun is a circle with a dot in the middle. So it's two solar masses, and the initial rotational speed, omega 1, is actually equal to 1.0 revolutions per 100 days, which I can go ahead and convert that to something a little more useful because it turns out this final velocity is going to be a lot faster, or this final angular frequency is going to be a lot faster. This is revolutions per, I don't know why I just did that, per 100 days. So I'm going to say 1 day. Oops, I don't want the day on the bottom. Let's say 1 day on top is actually equal to 24 hours, and 1 hour on top is equal to 3,600 seconds. So that's going to cancel out days with days and hours with hours. So that's going to give me revolutions per second, which is good enough for me. I could put it in radians if I wished, but I think revolutions per second would be fine. So if I take this, what I'm going to do is do 1 times 1 times 1 gives me 1. And then I'm going to take 1 and divide it by parenthesis 100 times 24 times 3,600. And this says 1 point, oops, changed colors and forgot about it. This says the angular frequency is 1.16 times 10 to the negative 1, 2, 3, 4, 5, 6, 7 times 10 to the negative seventh revolutions per second. So that's the initial one. But what they want to know is omega 2. So what I'm going to do is say 2/5 times 2.0 solar masses times 7 times 10 to the fifth kilometers squared. I'm saying I times omega 1 is equal to I2 times omega 2. That's what I'm actually using here. So 2/5 mr squared is what I just wrote out there. And now I'm saying this is all being multiplied by omega, which is 1.16 times 10 to the negative seventh revolutions per second, is equal to, again, 2/5 times 2.0 times the mass of the sun times 10 kilometers times, that's squared by the way, times omega 2. So we can immediately see that the 2/5 cancels out with the 2/5, the 2.0 cancels out with the 2.0, the m cancels out with the m, and all we really have now is omega 2 is equal to 7 times 10 to the fifth kilometers squared over 10 kilometers squared times 1.16 times 10 to the negative seventh revolutions per second, like that. So if I take 7 times 10 to the fifth squared and divide that by, I'm going to put this in parentheses just to be careful, 10 squared in parentheses. And now I'm going to take that. That's actually multiplying it by 4.9 times 10 to the 1, 2, 3, 4, 5, 6 times 10 to the ninth, actually. So I'm multiplying that times 1.16. Actually, ran into a problem here. Answer times 1.16 times 10 to the negative seventh gives me 568.4 revolutions per second. And we only had two sig figs, so I had to underline the rest of that. And a neat story, I can't remember her name. I couldn't remember her name in class today. I want to say her first name was Joyce, but anyways, a female astrophysicist was the first person to discover what we now call pulsars. And basically, what a pulsar is when you make a neutron star, sometimes it has these jets that shoot out very close to the rotation axis, but they shoot out linearly straight out near the rotation axis from the north part as well as from the south part, and that shoots out a jet of radiation. If that jet happens to sweep by our planet, then we see that jet of radiation hit us when it hits us, and then there's nothing for a long period of time. And then when it hits us again, and get another spike, and when he hit us again, it gets another spike. Well, she actually detected such a thing, and she saw it was on the order of hundreds of times per second. And she watched it, and it never changed. And therefore, she labeled it LGM for Little Green Men. What ultimately turned out to be was if you watched it for months, you would see that it actually did change a little bit. It wasn't hundreds of times per second and consistently the same value. It actually degraded over time. But what was going on was, in fact, just a neutron star that had a jet aiming towards us. And for that, she got nothing because she was a female. All right. With that being said, you can see in this case that this neutron star, which was originally just a regular star that rotated about once every 100 days, our Earth does on the order, I mean, our sun does on the order of one revolution per 30 some days or so. Not only that, it's what we call a differential rotation, so that the equator actually rotates faster than the poles do. That's sort of like if we were to look at a map of the or look at a globe of our Earth, for instance, we could see that, for instance, maybe the easternmost part of Florida possibly lines up with Martha's Vineyard directly above it. Okay. I'm saying rough order. There's some place in the United States that's directly above the eastern edge of Florida. So in general, you expect every year that will be due south. That section of Florida will be due south of that particular place at Martha's Vineyard or whatever. But if the Earth rotated like the sun did, then what you would see is Florida would actually move quite a bit faster than Martha's Vineyard did. And you'd come back and look a little while later and you'd see that, in fact, the tip of Florida is, hundreds of miles east of being directly below Martha's Vineyard. That's what a non-rigid body does as compared to the Earth, which is somewhat rigid, and that's why the location of something directly south of Martha's Vineyard in Florida, for instance, is always going to be directly south. Well, always over a human lifetime. Y'all know about plate tectonics, so that's all going to change as well. Anybody have any questions on this? Your book calls that 6 times 10 to the 2 or 600 revolutions per second. So that's pretty helpful. I do want to remind you about the rotational analogs. So your book are the rotational vectors, if you will. So the directional nature of angular momentum, L is equal to I times omega. Again, omega is defined to be the direction or have a direction that is perpendicular to the plane in which it rotates, and it obeys the right hand rule. So if the rotation is counterclockwise, the vector points up. If the rotation is clockwise, it points down. So now we're going to use that process to figure out example 11.4. Example 11.4 says, running on a circular platform. Suppose a 60 kilogram person stands at the edge of a 6.0 meter diameter circular platform, which is mounted on frictionless bearings and has a moment of inertia of 1,800 kilogram meter squared. The platform is initially at rest, but when the person begins running at a speed of 4.2 meters per second with respect to the Earth around its edge, the platform begins to rotate in the opposite direction as in figure 11.5. Calculate the velocity of the platform. So let me draw a diagram right quick to get an idea of what we're talking about. So the distance across here is 6.0 meters. There's a person standing right here at the edge, and the mass of that person is 60 kilograms. And initially, all are sitting perfectly still. But then all of a sudden, the person begins to run or perhaps dance. And now that person has a velocity v relative to Earth. V is equal to 4.2 meters per second. Again, that's relative to the Earth. Okay. But in doing so, he's running that way. That's going to cause the actual disk to rotate this way. Well, what do we need? We need the information they gave us. So diameter is equal to 6.0 meters, which means the radius is equal to 3.0 meters. That's going to come in handy. The moment of inertia of the disk is equal to 1,800 kilograms times meter squared. And the moment of inertia for the person is just mr squared, but we're just going to treat it as r cross p, so it'll be r times m times v. And we've got the mass of the person, little m, is equal to 60 kilograms. So if we treat the system to be just the disk, then we've got a problem because the human is actually applying a torque to the disk by running on it. If we assume the system is just the person, then we've got a problem because the disk is applying a torque to the actual person. That's what the person is using to take off and run, even though it's running with a speed relative to the Earth. He has to have some resistance as he pushes backwards. The disk's reluctance to rotate is what's pushing him forward. So that's clearly a torque on that. So we can't treat him as the system. So the system has to be the two of them. And initially, neither one of them are moving. So L initial is actually equal to 0 kilograms meters squared per second. Uh, Kilograms meters per second. Yep, and yeah, something like that. So that should be the units. But when they start running, what we have is L final is equal to basically the mass of the person, which is little m, times the radius, that's how far away he is, times the velocity that he has, the lowercase v, plus the moment of inertia of the disk times the angular velocity of the disk. Okay, so now I can set them two equal to each other. I was writing in purple, so I should probably go back to purple. I don't know what purpose, but anyways, we're going to say 0 is equal to mrv plus I omega. that means omega is going to be equal to negative MRV over I. The M is 60 kilograms. The R is 3.0 meters. The velocity is 4.2 meters per second. The moment of inertia is 1,800 kilograms meters squared. I dropped my negative there. So the answer is going to be negative 6 times 3 times 4.2 gives me 75.6 divided by 1,800, and I get 0.042. 6 times 3. Oh, excuse me, that's supposed to be 0.42. I multiplied 6 instead of 60. So this is negative 0.42. And since that came out, notice the meter squared cancels out with the 2 meters up top. The kilogram cancels out, and all we're left with is seconds on the bottom. I can throw in a radian because a radian is a pure number. So this is going to be negative 0.42 radians per second is equal to the angular velocity of the disk. The negative just indicates that, hey, if the person is running around it in a counterclockwise direction, then the disk is going to be rotating in a clockwise direction. Anybody have any questions on that? Okay. So, one thing I want to point out is omega is equal to 2 pi times the frequency. And normally, omega is measured in radians per second, but it could be other things. It could be revolutions per second or something like that. But radians per second is the preferred unit. But F has units of cycles per second, which is called a hertz. Okay, so if you're given something and they say it's in hertz, and you know that becomes the omega. If it's revolutions per second, that's sort of the same thing as hertz. One revolution is the same thing as a cycle. So that's why I usually refrain from using that. I would say maybe it's smarter to say not revolutions per second, but revolutions per minute, revolutions per hour, stuff like that. That is a good idea of what omega would be. I would say if it's omega, if it's revolutions per second, I would probably call that F. Okay. But you can see that the formula omega equals 2 pi F is merely just a conversion from cycles to radians. And that's what I was trying to point out to you. Anybody have any questions on that? Okay. Your book has a really good example called a conceptual example 11.5, and I wanted to explain that to you. So, conceptual example 11.5. So, what we're going to have here is a circular disc, something like that. What the heck? So we're going to have a circular disc. I'm going to draw a little smaller. And standing on this disc is a teacher. And the teacher is holding, and evidently just got a really long arm. Okay. He's holding this wheel that happens to be rotating in this direction. And according to our right hand rule, that means the angular momentum of that wheel is L, and it points up. Okay. It says your physics teacher is holding a spinning bicycle wheel while he stands on a stationary frictionless turntable. What will happen if the teacher suddenly flips the bicycle wheel over so that it's spinning in the opposite direction? So right now, L total is just equal to L. I'll just call that LB for bicycle wheel. Okay. But what's going to happen is once he turns that over, the wheel is now turning this way, and the angular momentum for that is, let's call LB2. That's going to be pointing down. But if we treat the system as the disk plus the teacher plus the bicycle wheel, then there is no net external torque on the system because the bearings on the rotating wheel are nearly frictionless, and there's no torque put on anything except through that friction, and we're ignoring that. There's air resistance possibly, but we're going to ignore that as well. So the total angular momentum must be the same. In this case, we've got AL total is equal to LB2 plus L disk. In order for that to be equal to L, that's LB by the way. In order for that to be the case, we have LB is equal to LB2 plus L disk. And all of these are technically vector quantities. I'm dropping symbols because I didn't necessarily need them, but it's probably best that I put them on there. So, in order for this to be the case, then you see that L disk is going to have to be equal to LB minus LB2. Well, we might call, if we choose to make a coordinate system like this, we might say that our coordinate system is the z-axis that way, the x-axis this way, and the y-axis that way. So with that in mind, we could say LB is in fact equal to LB K hat. Now LB2, since we're assuming he flipped it upside down, we're going to assume that he didn't speed it up or slow it down any. Therefore, the angular momentum of that case is LB as well. That's the magnitude, but this time it's in the negative K hat direction. So you can see that the angular momentum of the disk will be 2LB K hat. So what that means is by rotating it the way the person did with the wheel, now the actual angular momentum of the disk has to be in the positive direction, and that means the disk has to rotate this way. And that rotation will be such that I, which is the mr squared for the teacher, the mr squared for the disk, and the mr squared for the extra bicycle wheel, all of the, well, not the mr squared because it's not mr squared for anything but a cylinder, but the moment of inertia of each of those all added up makes the total moment of inertia of the disk thing, and that has to come up to twice as big an angular momentum. And basically, what happens is the disk is going to start rotating the opposite way that the wheel is now rotating, which is the same way that the wheel was originally rotating. Anybody have any questions on that?
I have a quick one.
Yes.
With the L disc part, you might be writing that now.
Uh-huh.
Uh, like which part of the diagram is the L disc
Okay.
portion?
Right now, I didn't draw anything on there, but you could write it like this and say this would be L disk. And it's the disk plus the person technically.
So in the first one, it doesn't equal LB plus L disc as well.
It does, but the L disk in the first part is zero because there's no rotation of the disk.
Oh, okay, okay,
Yeah, so the disk is sitting perfectly still. The teacher's also in that, and the teacher's sitting perfectly still. When I say L disk, that's just a short name for the disk plus the teacher, technically.
okay.
Does that make sense?
Yeah.
All right. So that's the explanation of all that, and that's you can actually try this on your own. It's actually kind of hard. I can't do that demo anymore because my shoulder's been replaced twice and doesn't work so well. I can just barely lift it up. So it's a little dangerous for me to go taking moving objects and spinning them up and down. But if you have a chance to do that, or if you have a chance to look online for someone demonstrating conservation of angular momentum, I highly recommend you do a Google search for that or a search for that on a YouTube platform, and you'll probably find a ton of videos of people doing exactly this. And you'll see that when they turn it over, the disc starts rotating the opposite way, or specifically, it starts rotating the same direction that the wheel was originally rotating before the teacher turned the wheel upside down. So that's just conservation of momentum, a linear or angular momentum. Anybody have any questions on that? That was a good question, by the way, Michelle. Section 11.2 is where they talk about the cross product. The only thing I want to say about that is there's a nice way of doing a cross product. I showed you that last time, but remember when you're doing a cross product, the two vectors that are being crossed together can't be parallel or anti-parallel. So you can't have I hat cross negative I hat or I hat cross I hat. You can have it, but it's just going to be zero, right? So with that in mind, you can never have uh, two vectors crossing each other that have the same direction, say, or have anti-parallel directions and get a non-zero answer. So that means you're always going to have a combination of one vector cross another vector gives a third vector. And if we break that down in terms of I, J, and K, we can say I represents 1. We can say J represents 2, and we can say K represents 3. And in order for you to have a cross product that is not zero, then the actual vectors that you can use in the cross product and the answer have to be 1, 2, and 3. So for instance, you could say 1 cross 2 equals 3, and that means I hat cross J hat is equal to K hat. And that's actually correct. It literally says 1, 2, 3. If you instead say J hat cross K hat, the answer has to be, in this case, notice you've got that's 2 and that's 3. The only answer that wouldn't give me 0 would be 1 over here, but that is not a cyclic permutation of 1, 2, 3. The cyclic permutation of 1, 2, 3 is 2, 3, 1, 1, 2, 3, 3, 1, 2. That's the only cyclic permutations. So this tells you that 2, 3 is going to have to be negative I hat. Similarly, if you did, let's say 3, 1, that would be K hat cross I hat. That can have a J hat right here, and that would be positive because that's a cyclic permutation. But if you had uh, I hat cross K hat, that's 1, 3, which isn't a cyclic permutation. So that means the other one's got to be the J hat, and that's 2, but it's not a cyclic permutation, so it's going to have to be a negative. If that helps you, then great. If not, don't worry about it. Just stick to using the formula I gave you, or using the cross product, using the determinant. Whatever way you find helpful, go for it. But this is just a way of figuring out what I hat cross J hat, I hat cross K hat, K hat cross I hat, K hat cross J hat cross K hat. All those are. They always have to be a cyclic permutation of 1, 2, 3 if they're all positive. If it's not a cyclic permutation, then the answer is going to have to be a negative. All right. Now that we have that, I don't need to do anything within this subsection because that's just showing you how to compute cross products. But what I do need to do is let me see. What is the angular minimum of a particle of mass m moving with speed v in a circle of radius r? Okay, so that's a conceptual example. Example 11.7. This one says, what is the angular momentum of a particle of mass m with a speed v in a circle of radius r? So what we know is m, v, and r. What we're saying is this is a particle of mass m. The radius of the circle is r, and the velocity is v. So L is equal to r cross p is the angular momentum. And in this case, since it's an actual circle, that means that the r and the v are perpendicular. So in this case, it becomes, if I choose to make my coordinate system this way, this would be x, this would be y, and then by the right hand rule, the z has to point up. Then I could say that L is r times m times v k hat. So that is a conceptual example of how to figure out exactly what omega is. Now, we also learned that the moment of inertia for a object orbiting in a radius of r is just mr squared. So we could, in principle, say L is equal to r times m times v times k hat. I could also interpret that as r times m, and then remember v is equal to r omega, so that could give me r times omega times k hat, and that gives me m r squared times omega, and lo and behold, you see that that is I times omega there. So that's another way of interpreting the angular momentum of an object, a mass m orbiting in a circle of radius r with a velocity v. Anybody have any questions on that? All right, I think that's just about it. Oh, the one thing I want to tell you is on what's actually equation 11.9. Basically, your book goes through the process of deriving this, and what he finds is that same Newton's second law that I told you. The summation of the external torques is equal to dl dt, and it said is valid only when tau external, the external torques, and L are calculated with respect to either one, the origin of an inertial reference frame, so it's got to be an inertial reference frame, and T and L are calculated about the origin, or two, the center of mass of a system of particles or of a rigid object. So you could also allow the axis of rotation to be the center of mass of the system of particles, and then it would work. So that's a key thing to understand. The other thing I wanted to point out is, let me kill this because we only got about 2 minutes left. This diagram right here, I really appreciate. Well, we already did this last time, so that's why I'm not showing that one. But I think what I'm looking for is this. This is the single best description I think that I've seen in any physics textbook, and this helps you understand exactly how, for instance, oh, I'm telling you to look at something that I didn't share. I'm going to share my screen now. Hold on. There you go. That's what I was trying to show you. So this diagram right here in your textbook and the paragraphs both above and below down here are extremely important. I want you to read them very thoroughly. I could probably spend 45 minutes explaining this diagram to you, and it would take me that long for me to explain it to in such a way that I think y'all could follow it really easily, or you can just spend the time yourself and try to read it and figure it out. I think that's worthwhile and it's really fruitful for you. So please, please, please do that. This example right here is another one I would normally do. So I want you to read that example as well. I'm probably going to discuss this example next time, but other than that, we're really done with chapter 11 because, as I said, those other sections, the Coriolis force and that sort of stuff, all that's I'm admitting you're not going to be tested on it. So we are done with chapter 11. I've already moved the due dates on the chapter 11 homework. So you still have, instead of it being due this Sunday, it's due, I think I moved it to Tuesday night at 11:59 p.m. or something like that. So you've got a little bit more time. Remember, we do have a online test. It was due Monday, and I just shifted it and sent an email to everybody. I pushed it back to Friday. That's in case I didn't even want to look and know, but that's in case any of you missed it. Make sure you knock that out. I also announced that our face-to-face test three can be taken as early as Tuesday of next week and as late as Tuesday the following week. And I sent an email with regard. I will send an email if I haven't already, an email regarding the actual times that you can sign up to have me proctor you either in class or via Zoom. So I've gotten some specific times I've listed. I'm going to send those to you in an email, and then you're supposed to let me know that by, I think I said like 8 a.m. on Tuesday the 22nd, I want to say. Whatever Tuesday is, I think that's the 22nd. It might be the 21st. But you guys are free to go. Thanks for coming. I'll wait for the last person to leave in case anybody has any questions. But have a good weekend. Stay safe and get your stuff done.
I had a quick question
Yeah, Michelle.
about the final exam. Like, do we have like a practice test or something that comes out with that?
Yeah, I'll probably be posting that Monday.
Okay,
But you'll always make sure students have around 5 to 7 days with the practice test. But yeah, I'll give you a whole different practice test for the final, and that
okay,
one's a little longer. Whereas these were like on the order of 5 or 6 questions. In order for me to be comprehensive for the final, the final exam practice test is usually a little longer, so it might have like 10 questions as opposed to 4 or 5.
okay. Yeah, no, I mean more is great just to like reiterate
Yeah.
it.
And the more you take it, every time you're going to get more or less different problems. So you get a more of an insight into what kind of problems you could run into. So hopefully that'll
Okay.
help.
Yeah, okay. Thank you.
You're welcome. What's up, Dylan? How can I help you, sir?
Yeah, I talked to you yesterday for the
Yeah,
class. I told you I'd be in here.
that's right. It was yeah, Fogelman, I think was your name, right?
Yeah, that was a different computer, so I had a different name listed.
Yeah, yeah. Yeah, the,
Um,
the Jasper and the Dylan's getting me. I was like, oh, wait a second.
yeah, it confuses a lot of people. That's why I usually try and keep it the same, but that was on my laptop and I couldn't remember how to change my name at the time.
Yeah, it's no problem. Don't worry about it, bud.
Um,
What can I help you with? What was the problem you were having?
I guess the first thing was on the first extra credit assignment.
Hmm.
I think two of the problems are being marked wrong when they shouldn't be.
Okay, let me pull that up real quick and look at it just to see what we're talking about. Uh, I've made so many questions lately, I can't just remember off the top of my head. So I'm going to pull it
Um,
open, and you're actually from 242, right?
yep.
Okay, so let me
So
open up a 242. I got that
it's
open.
question number six, where it says compute the left-hand side of Gauss's law and state the final answer.
Hmm.
And I picked 2EA equals 2EZA,
Okay,
which was following your video, and it
gotcha.
marks that as wrong.
Oh, then that's probably is an error. Let me double check. And like I said, you'll see there's so many questions that I made. It's a nightmare. Uh,
Yeah,
so
I think it's number six and seven, because I did also get number five wrong, but I can see why I got number five wrong, I think.
okay, gotcha. So 6 and 7. So that's this one. It says consider an infinitely large flat plane that lies in the XY plane and contains the origin XYZ. Assume the plane is a positive chart, blah, blah, blah. What I ask you here is calculate the left-hand side. This is for the infinite plane. That should be, oh, no wonder this correct answer is not right at all. It should be this. Yeah. Award points, correct, only award points for the correct answer. Give everyone full update question without regrading. I want to award points. Update. Okay. Yeah, the answer is supposed to be 2 E of Z times A. I
Okay.
all I can imagine is I accidentally clicked on it or something and made that the wrong answer. Make sure you send me an email or a text message, either one, because that earns you extra credit for finding that.
Okay.
Okay.
And then also number seven.
Okay, number seven is this one right here. And this one asks which charge density should be used for a thin again, that's a completely the wrong answer. It should be sigma equals a constant.
Yeah.
And I think that's what I gave on the last one. Who knows? But anyways, yeah, it should be sigma equals a constant should be that one. I don't know how it changed, but hopefully
I've
that
had that
fixes it.
happen on some of these where if you click anywhere or even sometimes scroll in the wrong spot, it'll change your answer without you knowing it.
Yeah, that's the problem. Like if I click right here, well, it's not going to do it now.
Yeah, I've had it. I've gotten questions wrong, and it's like I didn't pick that answer. Why is that wrong?
Yeah.
And it's like, oh, I guess I clicked somewhere, or I scrolled, or did something that changed my answer that I wasn't aware of.
Did you find that it was that the question sequence helped you better understand the derivation that I was trying to pull off? Because I mean, that's the whole
Yes,
reason I made
but
this. Go ahead.
I
What?
I had difficulty like interpreting,
My
especially
words?
like the beginning of it. Yeah,
Right.
because I'm better with like here's the problem and form. Like I can understand the mathematical side of it way better than like the I'm trying
Then
to figure out
put it
which
in
like
words verbally or whatever.
yeah, especially like the theory of it in words is what's hard for me. It's like when I see the formula, I understand it.
Right.
But then it's like when I'm trying to read it, I've just never been a very well good reader,
Hmm.
and reading comprehension has never been my strong suit.
Right.
Um,
Yeah, that's the problem with teaching physics in general. If you put the time in to put the sufficient wording to be precise and accurate and all that good stuff, it often gets so wordy that it's almost impossible for my students to read.
yeah.
So that's why I had to have something where normally once you get to say question three, question one and two have been exposed, the correct answers have been exposed to them.
Mhm.
That was what I was trying to do. But yeah, I see. Agree with that 100%. Very typical that students don't necessarily understand all those words I put in there. Hopefully, in reading it three or four times, they got a little better.
Well,
But
seeing that there was a video, must have overlooked that video that was specific for this. I
right,
hadn't seen that, and watching that, I was like, oh, okay, this makes it's word for word. Like it makes it a lot easier seeing you go through it and do it like that. Because
yeah,
I also like I got pretty confused like with the like where it says the proton should be at and it lists their locations and then it's like all right now imagine that there's three protons along this axis, three protons like just
yeah.
trying to visualize that and interpret what it's meaning really messed with me. I had difficulty understanding that.
Yeah, that was part I didn't go into as much as I wanted to in my lectures because it's really in the weeds, but I felt like I needed to explain to you why the electric field caused by this infinite plane is only going to depend on Z and that it's only going to point in the k hat and the negative k hat directions.
And see, that also is just trying to think of it that way. Being that we don't use vectors a whole bunch,
Right.
then it got brought back, and I was like, I remember these, I've seen these, but
Yep.
it's not like I hadn't used them enough recently to understand what I was actually being asked. And then it's like, even when you say it, I have to stop and
Think about it. Yeah.
okay, K, it's because it's okay, it's J, K, okay, wait. And then I have to like rethink over what is the order? It's I, J, K. So that's X, Y, Z. So then by then it's like I've been spent so much time trying to think of that.
Exactly. Like I don't even remember what I'm here for.
Yeah, it's yeah,
Yeah, I feel you. And
it's confusing.
I've tried to type this setup for probably 15 years now. I've tried to write it up like this, and I finally got, quote unquote, forced myself to get the time to do it. But it was literally these same things that you're bringing up is exactly the reason why I kept stopping because you get in the middle of it and you're like, God, this is so wordy that I'm not sure they're going to even read it. I've given out these in worksheets before. I've made them up in worksheets when I first started teaching, but I realized students would not read the worksheet at all.
I found there is a video. Have you
Hmm.
ever? I can't remember the guy, the professor, but it's like through the looking glass or whatever, and he teaches by writing on a glass essentially on the other
Hmm.
side of it.
Okay.
Um, it's and he does a very. I have a lot of his videos like I've been using, but he does a very good job of going through and like
And you literally
working.
say it's through the looking glass?
Actually, I can get you the right answer because that's something like that, but I have it on my YouTube. I can give you the right answer in
Yeah,
just
if
a
you could
second.
send me a link or something, that'd be great. I'd like to share that with my students so that they can all profit from that. I try to do my best, but to be honest
Yeah,
with you, there's a lot of people that have been doing this a lot longer than me, and they're more savvy on some AI stuff. I've been trying to write out AI stuff to get some of these concepts taught a little better. But
yeah, and that's what
I,
I've been using a lot of, and it's been helping a lot.
cool.
I basically copied in some of these what you said and was like, hey, can you dumb this down for me? And
Yeah.
it's like, oh, this is what it means, and I'm like, oh, okay, that makes more sense.
Well, I did have another student of mine tell me that he's been using the tutorial stuff that comes with the textbook. So, like when you first hit Open Pearson, when you're trying to go to the e-text, you'll
Uh-huh,
have these little chapter stuff on the left-hand side.
uh-huh.
He looked at that, and that actually had videos on more or less each subsection. If you use those, I hear they're really good too. I don't imagine that they'll go in as much detail as this guy did with Gauss's law, but if they did, that'd be great. But I'm definitely looking forward to you sending me a link to
So
this other guy.
his channel is called Physics with Professor Matt Anderson.
Okay,
Um,
Professor Matt Anderson, huh?
yeah, and he's got like modules too, where it's basically following our chapters.
Cool.
But he's got videos from like 10, 14 years ago.
Yeah, he's been out for a while. It's actually weird. I was among one of the first people to start in the system of physics where we actually wrote algorithmic solutions to problems and stuff like that. I used to be contracted by Pearson through my master's advisor. So I've been doing
Uh-huh.
this literally since 1993, but I never had any
This
video
is the year
stuff.
I
It
was
was,
born.
yeah, really.
Yeah.
Thank you for making me feel so much better. Now I know why my shoulder hurts. Well, that's cool. I appreciate that, Dylan. Any
Um,
other questions?
yeah, there was one on the homework I was
Okay.
going to ask you about. Let me try and bring it up real quick.
You're talking about this is 242, so let me go to a different
Yeah.
course so I can look at that one. And I'll go to 242, this guy. And what chapter homeworks that was it?
Um, Chapter 26 homework. Yeah,
26.
because that was why I hadn't submitted it yet, because I wanted your help with this problem.
Gotcha. Okay. I'm looking at the selections of the now video tutor bulbs connected in series and parallel. End of chapter problem 2616. Do you remember which number it is? Or
Uh,
RC circuit equivalent
7.
resistance? What's that?
It's
Seven.
7.
Okay, one, two, three, four, five, six, seven. What my computer says is number seven is, let me see if you see this now.
It's the circuit where we got to do the batteries and all that. You got to do the loop.
That one?
Uh, no.
Okay.
Yours is showing 9 of 15. Mine's
Oh,
7.
okay, so it's in nine. Gotcha.
Yeah,
This
yeah,
one?
that one.
Oh, yeah,
I
yeah,
did
okay.
it right in the example, and I feel like I'm doing it right, but I'm just not sure why I'm not getting the right answer.
Well, let me tell you, I actually did this Monday. I want to say it was Monday night. I worked this out for one of my students that came then. But let me work out the Kirchhoff's loop rule for the top loop and then for the outer loop. So I'll do this on the using this diagram. I'm going to go ahead and write it real quickly on my iPad and then share it with you. But what I'm going to do is I'm going to start from this point right here. You see where my cursor is?
Yeah.
I'm going to go around this loop in a counterclockwise direction.
Okay, and that's what
So
I did.
the first thing I do is plus 12.0. And notice as I move to the right in that middle leg, I'm going the direction of I2. So all my resistances should be voltage drops. So I'm going to say minus, the little r is supposed to be 1.0. So I'm going to say minus 1.00 I2 minus 11 I2. Now I've gotten to this junction right here and I'm going up this way. Notice that's the same direction as I1, so all my resistances will be drops again. So this is going to be minus 12 I
So
one. Go ahead.
um at that junction you're at right there, we're
Hmm.
right at 11 ohms.
Right.
So I2 stops there, I3 stops there, and since we're going counterclockwise, it becomes I1.
Exactly. Yep.
Okay, I just wanted to make sure. There was a couple times that confused me a little bit.
Yeah.
That's what I got too. That's what I
There's
got.
weird circuit analysis where you don't call one of those I1. It would be I1 minus I3 or something weird like
Yeah, that's
that.
how
That
it does
might
it.
be.
If you do this with AI, that's how it does it,
Yeah.
and
Yeah.
that
I hate
confused me
that.
more.
Yeah. So I've got minus 12 I1. Now I'm going across the battery and notice I hit the small leg of the battery and then the large leg. That's
So
what
it's
tells me it's a
plus.
voltage increase. So that'll be a plus 12.0. And now I'm going the direction of the current. So this will be minus 1.0 I1 and minus 22 I1. And now I'm back where I started. So I say equals zero. Uh, that is my first Kirchhoff loop rule equation, and that's for the upper loop. I'll just read it off to you again. It's 12.0 minus 1 I2 minus 11 I2 minus 12 I1 plus 12 minus 1 I1 minus 22 I1. So your equation should be exactly that or the exact opposite, like every negative should be a positive, every positive should be a negative.
Yeah, so I know for the next part where you combine like terms, I got 24 minus 35 I1 minus 12 I2.
Minus 12 I2. Yes. Yeah, and that seems to be what I remember getting as well. What I did at that point was I think I solved for I2 in terms of I1.
Yeah.
And yeah, okay. Now I'm going to do the outer loop and I'm going to start right here at this corner, but I'm going to do this whole loop right there going in that counterclockwise
Okay.
way.
Yeah. I did
Okay.
that too, just from a different point.
Okay. So with this one, I get plus 6.0. I'm going the direction of I3, so I'm going to say minus 1.00 I3, minus 18 I3. Now I get to the junction and run into the 12, and now this becomes current I1, which I'm going the same direction as I1, so that's good. So I'll say minus 12 I1 plus 12.0. That's because the battery. Minus 1.00 I1 minus 22 I1. Now I'm back to that next junction. I'm going the same direction as I3, so that's going to be minus 15 I3. And now I'm back where I started, so I say equals zero. So I've got 6 minus, well, let's combine like terms. I got 6 and 12 would give me 18.0. And then the I3s I add together, I get 1, 18, and 15. So that'd be 19 plus 15, that'd be 29 plus 5 be 34. So minus 34 I3. That takes care of that, and that. And then minus 35 I1.
Yeah, I got 18 minus 35 I1 minus 34 I3.
Yep. Yep, that's what I got as well. And then the Kirchhoff's junction rule, which I'll do for that right-hand junction, I'm going to say that is I3 plus I2 equals I1.
Yep, that's what I got.
Yep. So if you've got those, then you're doing everything right.
I
Now,
know the first time I did it, I had uh that equation I had messed up and I had included one that should have been I3 and I1.
gotcha,
So I had fixed that and I had gotten, I believe what I can no longer find out anything I've done wrong.
gotcha.
So that's what I'm gonna see if we get the same answers.
I
Because I
did
had
get
one attempt left.
0.51, 0.51, and then 3 times 10 to the negative third for the three currents. And
Oh, that is
yep,
okay, because I ended up getting 0.51, 0.51, and then like 2.7 times 10 to the negative third,
gotcha.
which
Yeah,
I only had one attempt left. And to me, that no, I didn't like those numbers. They were too close together and one was real small. And I was like, for my last attempt, I don't want to try this. It doesn't feel right.
Yeah, exactly. But yeah, that is specifically the answer. It's 0.51 for I1, 0.51 for I2, and then 3 times 10 to the negative third for I3. Uh, but the way I did
Oh,
it, just in case, it sounds like you were doing the same thing anyways, but I solved for I2 in that first equation, and that gave me 24 minus 35 I1, all of that over 12. And then I solved that second equation for I3. That gave me 18 minus 35 I1 over 35. Actually, that's supposed to be 34.
yeah.
Yeah, it's supposed to be
Yeah,
over
I had done
34.
all that wrong the first time.
Gotcha.
I had
I did
instead
work it
stopped.
on the end of the Monday video. Either that or it was Friday. It was Wednesday of last week. It's one of those two, but it's at the very end, and I completely worked it out and
Oh,
got the
okay.
answers and everything. So if you need to find it, you can see it there as well.
Okay. Um, I put in the chat a link to the playlist of that
Okay.
guy's videos for
Oh, cool.
Gauss's law that really helped me.
Cool. I appreciate that.
But he's got, like I said, he's got a playlist for pretty much each module that we have from beginning to end of this class.
Oh, that's awesome. That's sort of what I'm doing now is I'm currently trying to make a list of examples that I could do every semester, no matter what book I use, and be content with it.
Mhm.
Uh, I went ahead and showed you the equations just in case you needed to see it, but it sounds like you and I got the exact same thing.
I want to make sure that I actually did it right this time. 51, 0.51, 0.51, and then I3 is 3 times 10 to the negative
Negative third.
third.
Yep.
Oh, okay. I just didn't trust that answer enough to give it my
Yeah.
last attempt.
The way I work that, by the way, is I break those fractions up. Like I2 becomes 24 over 12, which is 2, minus 35 over 12, which I do that as a decimal
Mhm.
and just put it in as a decimal. And I do the same
Yeah,
thing with I3, and it
I
just
got
works out
that
pretty easy.
from one of your examples where you did that, the example out of the book, and you did it that way, and I liked it that way because trying to add it all in as a
Yeah.
long fraction like that would have just been really confusing for me. I hadn't even considered just making it, dividing it out into a decimal.
Yeah, I used to do it with all the fractions, which was cool, but you have to, I mean, the easiest way is to multiply through the least by the least common denominator, and
Uh,
then that cancels all the fractions, but then the numbers are so huge you don't want to touch it. You're like, "Oh, I got 1054 I1
yeah,
equals." So,
and I think for the last part is the terminal voltage, and for that you just use the uh
EMF minus 1
yeah
times R, I mean 1
yeah.
times I. Yep.
All right. Well, I think that was all the questions I had then.
Yeah, well, that's
Um,
cool. I'm going to go ahead since that particular homework problem was the set that you actually had some difficulties getting an answer from me in time. I'm going to change the due date to the 17th. So now once you submit, it'll count as full credit for anybody.
okay.
You included though.
When did you say the new due date is for the extra credits?
For the extra credit, I think I moved that today. You talk about the extra credit for the F2 for the face-to-face test that we were just talking about.
Yeah, yeah.
I think I moved those. Let me see real quick. I just changed the dates on them in one class. I'll make it at least the 19th. Maybe that'll be good. Yeah.
Okay, yeah.
Right now it says yesterday, but I'm going to move those to the 19th so people have plenty of time.
Okay, cool. Yeah, because I like to after getting through that video, it took me a while to get through the first assignment just to try and understand it and keep going back and making sure I was getting right. And
Right. It's
I
better
basically don't
to come
have
back and do
time.
them more, even if you can. So,
Yeah,
uh,
and I really only have time to do them on the weekends. I don't have enough time during the week to be able to put as much time into it as I would like.
right. Well, that's cool. I just changed the date to the 19th for one class. I don't, let me see, it might not even be your class. Nope, it's your class. Cool. Got that right. All right. Anything else?
No, I think that is it.
All right. Well, have a good one, Dylan. I'm glad you were able to make it back today, and I apologize for not catching your text this weekend. You have a good weekend and stay safe, and I'll see you next week.
Yes, sir. You do the same.
All right. See you, bud. Bye bye.